Before we get this episode of Science Night started, we should mention that, all of the YouTube viewers are seeing right now is a black screen, but they're hearing the sound waves coming from their speakers. That's pretty cool, right?
Yeah, absolutely.
It's the definite advantage that audio-only listeners have, is that they have to do this all the time. But if you're watching the YouTube video, bam, we just turn the lights on, baby. That's right. So shine bright and look sharp, because today we're going to be talking about light on the Science Nights. I'm Josh.
I'm Adam.
And light is a many splendid thing. Now, right now, we're being lit up by the electric lights in the
so there
studio.
Is trillions upon trillions of little photons bouncing all around this room right now.
Yeah.
Since we turned the lights on.
Yep. And also, like, the reflection of the white paint, around the room is bouncing more light than, like, say, if it was all green in here.
Right. Well, that's depending on which wavelengths it absorbs. It's more likely to absorb or reflect.
Yeah. But I guess we should probably start off with what light is. What is light? Light is love.
Light is energy.
Light is awakening. Light is intellect. Light is that light bulb you get over your head when you have an idea.
Light is far more than what we can see.
Yeah, that's true. So what is it? Light is electromagnetic radiation. It is the is it the byproduct of a nuclear reaction? Light?
Well, I mean,
if we're talking about the sun.
At the end of the day, everything's a byproduct of the Big Bang.
Right.
So.
Okay.
But it's energy. So anything that releases energy will release electromagnetic energy.
Yeah.
Photons.
Could
release photons.
Most combustibles do that. So like a fire, it'll use chemical energy to use heat and light as a byproduct, or has heat and light as a byproduct. But light itself comes from a specific range of the electromagnetic spectrum. Visible light is a very, very small amount. The stuff that you're seeing coming through your television screens. We're not even there. Your YouTube phone screens. Although YouTube doesn't make a phone either. You know what I mean. It's all within the visible spectrum, which is like just a chunk, just that stuff you see through a prism.
Right. Well, and everything you see, but
yeah, as well. But it's so much more than that. There's longer waves past the infrared end that make up radio waves, and then there's way shorter waves past the ultraviolet end that make up X and gamma rays, which are harmful.
Yeah, absolutely.
Light is awesome and deadly, and is the universal constant. It's so many things.
You mentioned microwaves. Everybody has a microwave in their house.
Yep, it's contained in a Faraday cage.
Yeah, absolutely. That way you don't get the microwave spilling out into your kitchen.
Absolutely. It resonates, or what does it do? It evaporates water internally, and it's one of the things a microwave does.
Right. Well, yeah, it starts to vibrate all the particles that make up the whatever you're heating it up.
Sure, and then that just leads to regular evaporation.
It does not cook from the inside out, which is a common misconception of.
Really? What food does cook from the inside out? Nothing?
Nothing. Because
that's impossible, right?
The heat source would have to be inside the food for it to happen.
Humans, we cook from the inside out. 98.6. I guess the important part is how does light work? What happens? So you have a source of light, and it sends out photons, and photons do this wonderful thing where they act as both a particle and a wave. And we're going to hint a little bit into quantum mechanics here, but then we're going to go right back into the practical world, just because I don't want to confuse myself in the into that. So a photon acts like a particle in that it's a small amount of something.
Right. It's a thing. It's a photon. So.
And it has mass, or it has volume, but it doesn't have volume. It's this weird little thing. But a photon is a particle, much like an atom is a microscopic particle, or an electron is a subatomic particle.
Right.
A photon is a particle.
Absolutely.
But it behaves in a wave manner. So when we talk about the electromagnetic spectrum or an electromagnetic wave, for the YouTube audience, you'll see what I mean by that in the form of a wavelength. So that's how a photon moves through the universe. For you audio listeners, think of like the sine curve in mathematics, or a wave.
Yeah, well, yeah,
wave.
any kind of wave. So if you think of the standard like wave diagram, it's just showing
Peaks
the
and valleys,
oscillations
peaks and valleys,
of energy, and then along a time period. That's why it's length.
Yeah. Because anytime you measure it at any one point, it's just going to be here or here, and then you draw the timeline.
Right.
But the reason it's so the quantum mechanics part of this, Adam, can you help me get into this part just to touch it, and then we'll leave it alone.
Well, I mean, we kind of did. That's
we did. Okay.
That's the point. I guess what you're thinking of is when we were talking about like the double slit experiment. I feel like we've talked about that on a previous episode.
I imagine it was with you and Peter, or you and Garrett.
Either Peter or somebody else.
Steven?
Maybe, but I'm not 100% sure on that. But we did talk about it a little bit, and I'm sure you can probably put up like a GIF of it or a video.
Sure,
of
I'll
it
put
or
up
something
an
like
image
that.
and video of the double slit experiment.
But basically, it's proof that that light acts as both a particle and a wave.
Okay.
You know, where the quantum weirdness comes in is where, you know, when you observe a quantum particle, it acts different than before you observed it. Right.
So, okay, so the Schrodinger's cat thing, it's alive and dead, but you won't know for certain until it's...
Pretty much, yeah. That's pretty much the basis of that weirdness of quantum mechanics.
One of these days you'll find someone to talk quantum mechanics with, and I'll just be sitting here making sure it looks nicer. But let's see. So what happens when, let's say, it's daylight outside, or an electric light source is around you, and it hits something red? So there's the red of the thing behind you, the curtain behind you. So what's happening is that white light, all light, is hitting the curtain and reflecting red back at us. So we see red. The chemical processes that go on with our cones in our eyes interpret the light bouncing in as red.
Right. So
and that sends that signal to
the
our
material is absorbing more of the other wavelengths of the visible spectrum.
Yeah, and bouncing red back at us.
Right.
The same is true for the orange on my guy's shirt, the blue of Adam's jeans, even the black of your hoodie.
Right.
It's just, that's just how it works. It's might be a little hard to wrap your head around that, because you'd think that I colored that red, like it's dyed red, like, you know, but that's how it is working.
Well, you know, there was a time in history when people thought that some sort of beams came out of our eyes and reflected back off of the right, and that's how sight worked.
Yeah. Like we said earlier, the visible spectrum is what we as humans work off of, and you're like, well, why is that? And it's because we evolved that way.
Wow.
Our ancestors came out of the sea, and in the sea, light travels for a lot further at a certain wavelength, at a certain range, and it's 400 to 700 nanometers if you want to get technical. So we evolved there, so the first light we were exposed to was there, and since it worked and kept us alive, there's no need to change it. There's no need to adapt. Nature selected this form of our lens. Now it has become further and further complex since then. We've developed a lens. We have an aperture that, like, the first eyes were just a hole.
Yeah, we're just a light sensing cell, basically.
Yeah. And then, you know, we developed muscles around our eyes to, like, that's an aperture, like a focuser. Like, we have a lens. You have a lens over your eye. I mean, you have an iris, which holds your color cells, which you're allowed to, you know, you see because of the rods and cones around your pupil. But yeah, it's a chemical process that happens because of your interpretation of a wavelength. It's crazy, right? Like, to boil it down like that, because to a lot of people, they would describe, like, when you're looking someone else in the eye, they're like, when you see these, like, you see the intensity of the emotion, but really all you're seeing is light reflecting back at you.
Right.
Like I will never experience atom in the now. I will experience atom in the milliseconds or nanoseconds or microseconds it takes for light to bounce off you to get to me.
It's true. It's true. Yeah, you can think of it that way. It's just it's such a small amount of time that it doesn't matter, right?
Sure, but if you're looking at this,
but there is a slight delay between what you see and what's actually happening. Yeah.
What about this? Snap. Like you see the act before you hear it.
It's true.
Light travels so. Let's say that I had done that at a distance of like 20 feet. If I could snap that loud, you know.
Right.
You would see me do the action before the sound got to you. It would be like half a second off.
Well, and it's happening even at this distance that we're apart from each other, but it's just such a small difference, you know. Yeah. We can't detect it. You could maybe measure it with, you know, equipment
that we don't have. But or know how to use. To be honest, I wouldn't know how to use it.
That's what Google's for.
Yeah, right. I like that though. It describes one of the most important properties of light. There's A, it's the fastest thing in the universe, and B, it's constant. I don't know if it describes that second part, but that's what it is light is always traveling at a constant speed.
Well, yeah, the universal constant. So I think it's technically incorrect to say that light is the fastest thing in the universe because there are other things that move at the speed of light.
Okay.
That's why it's actually incorrect to say the speed of light. It's the constant speed of the universe.
Okay.
And just light happens to move at that speed.
Gotcha.
But yes, you're right. It's constant in the sense of that a photon is created moving at the speed of the constant, the speed of light. You know.
Okay.
It doesn't accelerate to it.
Yeah, it's always there.
Right.
Yeah.
Right.
Yeah, I didn't think it had to like start your engines.
Which is also the reason why a photon is massless, since it can move at the speed of light.
So mass can approach.
So I don't know if we've said this before. I know we've kind of talked about it, but there's like a little, almost a joke because there's no perspective of a photon or anything like that. But the idea that everything in the universe is happening at the same instant for a photon.
Sure.
Since it's moving at that speed, time has slowed down to a complete stop.
Yeah, it's a stop.
You know?
Right? Yeah. That's interesting to think about.
It's an interesting kind of thought experiment or whatever,
right, yeah.
But it's not technically correct, right? Because a photon doesn't have a perspective. But
sure.
Well, a photon doesn't have it's massless, so it doesn't have a frame of reference, you know, an inertial frame of reference.
It can't know itself. Like it doesn't recognize its own perspective, right? So speaking of perspective, light, like you can't, like, okay, a couple things. Thou shalt not travel faster than the speed of light. Like humans won't be able to do it, I don't think, ever, unless we become photons ourselves. I don't think we'll ever be able to travel as fast as the speed of light.
No.
But we can manipulate light in ways that I think is interesting. For instance, refraction. We know that we can bend light. It'll still move at the same speed, but we can bend it. And an easy way to demonstrate that is you get a glass of water and you put a straw in it, and you'll see a parallax of the straw.
Right.
It's refracting the light.
It looks like the straw isn't connected inside
inside the glass. That's really simple way to demonstrate it. We can use refraction in very important ways. One of them being telescopes. We use refraction telescopes.
Absolutely.
That's how we see so far. We bend light into it, and we can bend, and then we're able to see out of it.
In refracting telescopes, you should be more specific. Because a standard, like a basic Newtonian reflector, I guess, isn't really refracting because it's not moving through any lenses. It's all bouncing off mirrors then.
Gotcha.
Well, actually, I guess it would be moving through the lens and the eyepiece still. So there's always still a little bit of refraction going on. Yeah.
Magnifying glasses use refraction. Contact lenses use refraction. Microscopes use refraction.
Yep.
Pretty much anything that goes through, like light is refracted naturally through your eyeball. Light is also naturally refracted through the atmosphere. Especially if there's clouds, right?
Because
like we talked about on the Flat Earth episode, how the sun looks like it's going all different directions, but it's hitting us parallel.
Right.
Like all the light's hitting us parallel. But when you see the God lights that I call them, they look like the fingers of God, coming down from the
right, like the God
clouds.
rays or whatever.
Yeah, exactly.
Yeah.
So you can see them sometimes in like massive patterns, or like, but that's just because it's refracting through water in the atmosphere, or it's refracting through our atmosphere itself.
Things can affect light. So like when we talked about, the speed of light, that's in a vacuum, right?
Yeah, it is.
So if it's moving through water, it slows down a little more. The atmosphere slows it down a little more. And like we talked about, also gravity can also affect light. So that's one of the reasons like we know about dark matter.
Okay.
Because dark matter we can't see physically, but its gravity is there's enough of it that it has enough gravity to bend light. Same with large, black holes, large galaxies, clusters of galaxies can bend the light from like more distant stars around them.
So it would distort the light coming to us because there's something in the way, or something close enough in the way that it bends it.
Or
is enough gravity.
Because it's so massive that it has enough gravity that it's altering the course of that photon.
Yeah. Okay. Heavy stuff
around it,
Yeah.
Same way anything would orbit around anything with gravity,
because
just anything with mass. So
yeah. Now we have to talk a little bit about some of like we did in our first few episodes. We have to talk a little bit about some of the important discoveries around light. The first one being that the first conscious human opened their eyes and they were like, I can see. But no, the visible spectrum was actually Newton. He started playing around with a prism, and he was able to separate light into what we know as the visible spectrum. Roy G. Biv,
Right.
Go ahead.
No, go ahead.
Okay.
You're on the
It was his experiments in optics that first made him famous. That's what got him notoriety in the first place.
Right.
It was like, he found light. And then, later on developed calculus and made physics a whole thing. I also want to talk about infrared light. So that's about 150 years later after Newton. And it's Sir Frederick William Herschel. We actually talked about him during the astronomy episode.
Yeah.
But this guy was born in Germany, and he wanted to test the heat of the electromagnetic spectrum. So he put, he got a controlled room and controlled environment, put a prism in front of the window outside, the window to the outdoors, and he set up thermometers along each of the colors, and then he set a control outside of the range. Well, he came back to find that the control had gotten warm, just like the red one had, but a little bit warmer.
Right.
And he discovered essentially that there's invisible light, and so he called it the infrared spectrum. And then further down the line we discover alpha rays or we discover gamma rays and X rays and all kinds of stuff on the ultraviolet side of things, as well as the cosmic background radiation that's from radio waves. Like way out in the universe, waves that are hundreds of feet long. Am I wrong in that?
Yeah, those would be radio waves first put out by the Big Bang would be the cosmic radiation.
Yeah. So I'm not wrong?
No, you're right.
Nice. Yay. So I don't know, it's crazy to think of, like, I know that there's more discoveries that we can talk about. We were only specific on the two there, but just think of the people that were like, what else is there for light? And then you just like SETI uses radio waves to look through the universe, right? So they're not listening, but it looks like they're listening, but it's radio waves. So they're just 500 meter long is their wavelength or something like that.
Radio waves have a pretty big spectrum.
Yeah,
they're the largest of the wavelengths of the electromagnetic spectrum.
Yeah, so
I mean we use radio waves for everything, right? Like the Wi-Fi in this room, the you turn on your stereo in your car.
Yeah, absolutely. They exist within the frequencies of one. Okay, so wavelengths can be 1 millimeter to 100 kilometers.
No,
I don't know. Like that's how weird light is, right? Like you're using light to reverberate sound. It's crazy. I don't know. It's one of those things that light is fantastic, but it's almost like mythological in its ability to do things.
Oh yeah,
Because it's so much energy.
Yeah, exactly.
It's just all energy.
I think it's so. What makes it hard, right, is that the whole electromagnetic spectrum is much larger than what we can comprehend on our own.
Sure.
You know? So we have to require help or tools or whatever you would, instruments to record it.
Yeah.
It's also very ingrained into our evolution. So
light, how important it is.
Yeah.
Yeah.
Light and the heat from the sun and anything like that. The way our skin is built to try to protect us from UV rays.
But also uses light and a certain folic acid to create vitamin D.
Right, and that would be how our body reacts to it.
Yeah. So we need light on a biological level. And that's like solar radiation that we need. It's not like electric light. We don't need electric light to make vitamin D. We can't.
No. Yeah, you're right. Yeah.
The last thing I want to touch on is something that we're actively doing right now, and we're capturing light through a couple different cameras, accompanied by our voice capture audio stuff. Light going through, basically a camera is a mechanical human eye, right? A mechanical human eye with a hard drive. Now,
right?
It didn't used to be. The film was you had to imprint on it, but
there's a cell in the back of the camera that's basically similar to how film works.
Okay, I didn't know that. I the reason I wanted to talk about it is just because a camera is capturing light, and it's like a one-time thing. It used to be a one-time thing.
Right.
Right now we're
film camera.
Yeah.
Right.
Right now we're capturing 30 frames a second of digital footage, right? But it's still essentially the same thing. We're capturing light just through a digital means as opposed to an analog mean. And then when we play it back at 24 frames a second, it looks like real motion.
Yeah.
But the audacity of someone to be like, I think I can make this last, and it's not a painting, and just imprint enough chemicals onto a special kind of paper, and just capture the negative of the light, and then recreate it. It's incredible. The basic technology that makes it all possible is still fairly simple. A still film camera is made of three basic elements: an optical element, the lens; a chemical element, the film; and a mechanical element, the camera itself. As you see, the only trick to photography is calibrating and combining these elements in such a way that they record a crisp and recognizable image. So normally now, most digital cameras will just have an auto setting that kind of handle that focus and stuff on their own. But you can still manipulate that, even with your phone you can. There are different ways of bringing everything together. One of the things we'll talk about is a manual single lens reflex, an SLR camera. That's what most photographers use an SLR.
Yeah.
It's mostly now DSLR. It's all digital. But there are still people that manufacture single lens reflective cameras or reflex cameras, and they still do use film.
With film based, you mean?
Yeah.
Very few, though. I don't know that. I mean, I'm sure that there's still those people that are held out film.
Film for life.
The pure way to
film
go
forever,
or whatever, right? But I would imagine
majority is digital.
In today's day and age,
yeah.
Most people have gone to. I remember when I was first interested in photography, that was just at the very beginning of digital cameras, and that was still when a lot of people kind of thought that it's going to be a long time before this technology matures to the point of capturing the same quality image as film.
Sure, yeah. I remember when digital cameras were crap.
Yeah.
Real bad. You could take a 420 by 240 image and then maybe pull it up on your camera, maybe, or on your phone. But then eventually people were like, "Oh, look, it's got 4 megapixels," and you're like, "Wow."
Right. But now, I think that the digital, the chip on the back of a digital camera has gotten sensitive enough that it's now surpassed film.
Yeah.
So.
Which is why we can shoot in 4K and we can shoot in we can project in 4K as well, but that's different. That's a different way of shooting light.
We can take for the most part we can take higher resolution images. Resolution doesn't really equate exactly to film, but
yeah,
higher resolution, higher quality images than you can in film, except for maybe really large format film still.
IMAX.
So like, if you the bigger the bigger the photo,
the 75 millimeter versus 35 or whatever the really cheap stuff is.
Well, 35 millimeter, is like what we would use in not modern, in an old camera, you know.
Yeah. Let's see. So it should also a single lens reflex is a camera that the photographer sees is what the photo is going to be.
Right. That's why professionals use SLRs.
Yeah.
So they can, because you're seeing exactly what the film is going to see, or the the digital chip in modern times, but you can see exactly what it's going to see, and you can put the same kind of like changes in aperture and focus and stuff on it. A viewfinder is always a viewfinder on a like a point and click camera is not accurate.
Yeah.
To how the camera it's not 1-to-1 exact to what the film is what the actual picture is gonna be.
Okay. So the optical part of the camera, in any case, is the lens, and what it does is it's bending. All it is a curved piece of glass, and its job is to take the beams of lights that are bouncing off an object and redirect them together to form a complete image. An image that looks just like the screen that's in front of the lens. It's supposed to be photorealistic, right? It is. That's the lens's
it's because
job.
It's put in so it's just a regular standard point and click camera. You've got the lens that's actually taking the picture, and then you've got the lens that you look through.
Yeah.
Right?
Okay.
Which are two separate, completely separate lenses. You know?
I didn't know that.
On an SLR, there's a little mirror that's flipped up, so you're looking through the main lens of the camera.
Gotcha.
You know,
like a periscope.
And as soon as you yes, exactly. Yeah. And as soon as you take the picture, it flips that mirror up, lets the light go straight through to the film, and then flips that mirror back down. Yeah. That's what that clunk clunk noise is on an SLR.
Gotcha.
You know?
That's a mechanical thing.
It is, absolutely. And if you're doing really sensitive photography, like astrophotography, where you need to keep the exposure open for a long time, you want a camera that you can lock that mirror up manually. Yeah. So you lock it up first, and then you start the exposure, because that little movement of the mirror is enough to mess up how focus? Sensitive.
Okay.
Yeah.
Cool. We started with light and ended on cameras. It made sense. But I'm sure there's plenty that we got wrong tonight. And, hey, thanks for bearing with us through the break that we had for Thanksgiving. I hope you stayed strong and found some science of your own. You probably did. But we'll be back again next week with something new in science. And we always appreciate peer review, so bring it on.
Yeah. Absolutely. Light is just such a huge topic, right? Like, there's no way we could cover everything about it, and especially with we just barely scratched the surface on a little bit of quantum particle physics there,
and then rambled through how a camera works. But that's all right. We will see you guys next week on the Science Nights. Bye.
Bye.